So a lot of IB students struggle with proof by induction, but all it really is, it's just a method that we use to prove statements like this when we can't really find another way to prove it directly or prove it by contradiction. So all we really have to do is just follow this three-step process. And even though some of them are very difficult to see and very difficult to work out, if we just stick to these three steps, we should be pretty fine with enough practice. So our first step is our basic step. And all we do in our basic step is we let n equal to 1. Okay, what that does is it gives us a base case, right, to show that both the left hand and the right hand side are equal to each other for at least one value. So we sub in something simple like n, 0, or like 1 or 0 or whatever, depending on what the proof is and depending on what the starting values are and depending, obviously, what the domain is. So all that is just a basic step, right? Just showing that both the left-hand side of the equation and the right-hand side of the equation do equal one another for at least one case. The next step is the assumption. And it's kind of a hard concept to understand, but all we really do is we just assume that the statement is true for some value, right? So for some value of k. That is also a part of the integers. Okay, all we're saying is that we're assuming that the statement, right, the statement above is true for some value k. And all we do is then rewrite the statement in terms of k. Now, the next step is the inductive step. And what we do here is we let n equal k plus 1. So what this is showing is that for the next term, right, showing for all terms, right, k and k plus 1, that it's true, right, the statement is true for everything. Okay, so in our assumption, we assume that the statement is true for any integer k, right? We are just saying that the statement is true for any integer k. Then the inductive step tells us and it shows us that the statement is true is really true for all positive integers, right? And showing it that it's really true is adding 1 to k, right? K can be any term, and if we add 1 to it, then we're adding 1 and showing it's true for a next term, right? Hopefully, right? That is the goal. Okay. So we're going to take this statement above and prove it by induction. All right. So let's go to a new page. So let's run through our process. We want to prove that 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is equal to n squared plus n plus 1 squared. N squared times n plus 1 squared divided by 4. Now, so let's start with our basic step. And remember, we let n equal 1. So for our left-hand side, that's just 1 cubed. And for our right-hand side, we sub in 1 for all of the n's. All right, so 1 cubed is just 1. Then we're left with 1 times 2 over 4, or 1 times 2 squared over 4, which is just 4 over 4, which means 1 is equal to 1. And our left-hand side is equal to our right-hand side. So we now have a base case that shows that this is true for at least one value that's a positive integer. Now, next step, okay, is our assumption. So we assume that n is equal to k for some k that is a positive integer. So now we sub k into our original statement. And all we're doing here, we are just saying it's true. That's it. We are just saying it's true. All right, it is true. Okay, 1 cubed plus 2 cubed plus 3 cubed all the way up to k cubed is equal to k squared times k plus 1 squared divided by 4. All right, that's all we do for our assumption. Now, the inductive step, k plus 1. We let n equal k plus 1. Okay, so we sub in k plus 1 into the statement. Now, before we get into the math here, it's helpful to take our original assumption, okay, k squared times k plus 1 squared divided by 4. And imagine what would it look like for k plus 1. All right, so now for all of the k's we have here, sub in k plus 1, and what we get after that is what we should hopefully get after assuming n is equal to k plus 1, right? So through a bunch of algebra, through a bunch of combining like terms, right, factoring in general, we are hoping to end up with a statement that looks like that. All right, so I'm going to keep this up here in the corner as a reminder of what I want to end up with. And now what I'm doing is subbing k plus 1 in. Okay. So within the sum up to k plus 1 cubed, there's also the sum up to k cubed, right? Because k cubed is the previous term to k plus 1 cubed. And we are adding all the terms up all the way up to k plus 1, and that includes the sum all the way up to k cubed. Now, the assumption we made up top, all right, all the way up here, is now apparent in our inductive step. So since we assumed it's true, we are now allowed to sub in what we assumed above for our sum up to k. All right, now I'm running out of room here, so I'm going to have to carry this over. Or I should I'll bring all of this over. Let's go to new page. Okay. So once we're here, now it's just a matter of factoring and trying to get back to, remember, our goal up here. All right. So a good rule of thumb, anytime that you see like terms like this k plus 1 here and this k plus 1 here, it'd be a good idea to factor them out immediately. All right, so since k cubed also has k plus 1, I'm going to factor out a k plus 1 squared. So I'm left with k squared divided by 4 plus k plus 1. Now, I don't like working with fractions, so I'm going to take out that 1/4 as well. And now I'm left with k squared plus 4k times k plus 1 within that parentheses. So now, just distribute u4, continue to simplify, and I'm left with 4k plus 4. Now, k squared plus 4k plus 4, that's a perfect square trinomial. right? So remember, if we have x plus y squared, right, that comes up to x squared plus 2xy plus y squared, right? And we can take k squared plus 4k plus 4 and rewrite that as k squared plus 2 times 2 times k plus 2 squared. Right, it's running out of room a little bit there. But that's where we get this next step, which is the last step in our inductive process here, which is factoring that quadratic to k plus 2 squared, right? And if we notice, we've arrived at our goal earlier. So by the principle of induction, we have proved that is true for any value of k.